We are starting with a new chapter, and the chapter is magnetostatics. So far, we have covered in the two chapters the electrostatics. In chapter 2, we started the electrostatics from Coulomb's law, then electric field, then electric potential, Gauss's law, and we went on calculating the force between charges, and those charges were at rest. So the charges they were at rest, and we studied electrostatics. The source charge, you can say it is at rest. The stationary charge can be at rest. It can be moving as well, because when it will experience the force of the field by the static charge, then it will move. So, uh, in chapter 3, we then discussed the electric field and later, and now we are in chapter 5, which is magnetostatics. Now, why this magnetostatics started? So, if I do consider different charges and there is a dust chart, like for example, we are having different charges like they are Qi, Q1, Q2, and so on. And there is a dust charge Q. Then this charge will experience force from these charges, and with the help of superposition principle, we will calculate the force on this test charge from these source charges. The source charge may be one or more than one. So it will have force from this one and from this one and this one, and we will do calculate the superposition principle all the force of these charges. So when this test charge is in the field of the source charge, then it will experience a force and it will move. We consider the test charge is a unit charge, and with a negligibly small magnitude, we consider this test charge. Now when I come to a situation, and a situation is this one here, we know that single charges will repel each other. They will repel, and the opposite charges, they will attract each other. And this is what we established in chapter 2. Now we consider a situation, and the situation is that we have a source, a potential source, a battery, and we connect wire with this one, like this terminal is connected to this wire, and then it is fixed somewhere here, and the current then comes back to this terminal. This is a conventional direction of the current, and we see that these charges, when we consider that in motion, then these two wires, current is going in the opposite direction in both. So they start repelling each other, unlike the situation in which singular charges were repelling. Now, singular direction of current here, if the current goes in this direction and come back in this direction, so it's the opposite direction. Now, if here we just manage this one like this, that the current goes from plus and then it comes here, and then it moves this way. So now the current basically is going in the same direction, because in this one the current goes this way, and then in this the current goes in the same direction. So same direction conductors, we see that they are attracting each other. Now, from where this force arises, that if the current is going in opposite direction, that they are repelling each other, and if current goes in the same direction, then they are attracting each other. Now, whether this force is electrostatic in nature, so here the charges are basically moving. So it's not electrostatic in nature, and it is opposite to that one because similar charges were repelling each other. Now, if I consider this situation, let's say for example, these are copper wires. Now they are neutral because we know that the positive and the negative is valence there. Although we know that there are free electrons, there are loosely bound electrons in copper. So, but the net charge on the copper is zero. So it is neutral. So they are basically neutral. Then why they are repelling each other? It's this question. So we say this when they repel or they are attracting each other, the nature of the force is not electrostatic. And the but the conductors, they are basically neutral. So from where this force is arising, and we call that this force is basically magnetostatic force. This is magnetic force. And the first time that we toss up the name magnetic force. So magnetic force is responsible for this attraction and repulsion. So we say that when a charged particle is at rest, then it will generate electrostatic force. It will generate electric force. But when the charge start moving, the gate charge will have, in addition to the electrostatic force, it will have magnetic force as well. And we encounter this thing for the first time when we move the charge. So there, let's consider that we want to calculate the force. So the first thing is the direction of what is the magnitude of this force, and then the direction of this force, what it will be. We write this force by the, we know about the electrostatic force that it was equal to F times QE. R, this Q I'm writing generally because here, if you use the test charge here, then F over Q is the electric field here. So the electric force is equal to this one. Then what is the magnetic force equal to? So this magnetic force is equal from the Lorentz Force Law, F equal Q, and then V cross B. V is the direction in which the charged particles are moving. And B is the magnetic field which is generated due to that movement. And F is the force which this field will cause. And this is the magnitude of the force. So I can write for both here. There's Lorentz Force Law for the electromagnetic force will be Q and E equal V cross B. Now the nature of this force is, it is the result of a cross product. The cross product means that it will cause rotation, it will cause twist here. This force will be causing rotation. Look here, as we say that when for the direction of this force, when we say that vector C is equal to A cross V, two vectors A and B, and if they are having the cross product with one another, that C is their resultant vector. Now this C is perpendicular to E, and this C is perpendicular to B. Is this C is perpendicular to the plane which is containing A is B. So it will be out of the plane. Now here, if I consider that this is a wire in which current is flowing in this direction, then I is means the motion is in direction V here, the velocity of the particles, and B is into the boat. So here, if I consider the XYZ coordinates, you will remember one day we say into the board with across and out of the board for the magnetic field is a dot. And I hope you know that why we use this, because if the arrow is coming toward us, like if the arrow is coming out of the board, then we will see tip of the arrow, the hand or tip of the arrow, and it will look like this dot here. And when the arrow is going into the board, so we will see the cross of that arrow, the beak of that arrow, and it will be the cross here. So magnetic field is basically here into the old this one. So if I give direction to this one, then V is along the y-axis and B is along the A to the both. So this is minus Z. And what about V cross B? This V cross B, when we y cross z when we x and minus x. So it is in the minus x direction. So minus x is in this direction. So minus x is in this direction, and this would be the direction of the force. So the force is in this direction. So this was the Lorentz electromagnetic force creation. We will have to keep some historical background in here. This person, a Dutch physicist, Hendrik Lorentz, whose relatively Lorentz transformation is also very famous. So he's the same person and a Dutch physicist who did this, but the credit basically goes to Oliver Heaviside. Oliver Heaviside, the student of James Clerk Maxwell, because it was Oliver Heaviside who developed a fair calculus, very simple calculus, and he reduced the quick equations of Maxwell into four elegant equations. Elegant and simple equation. So this notation also goes to Oliver Heaviside, who did this thing in a very elegant manner. So here we have this E V cross B, and this is the magnetic force. One thing we will have to see here is for the footnote of G.J. Griffiths. One footnote is related in the fourth edition to the historical background of Oliver Heaviside, and the other footnote is related to the pseudovectors, that why the magnetic field is treated as a pseudovector. So keep in mind one thing. There, when we say pseudo-vector, pseudo-potential, pseudo-function, when a vector does not satisfy all the criteria which is for vectors and it behaves like a vector, then we say that it is a pseudo vector. Similarly, a potential, similarly, a function, when it is not fulfilling all the criteria of a function, we call it a pseudo function. So there are two types of vectors here. One we call is actual vectors or polar vectors. And polar vectors are basically, for example, force. Force is in actual vector or polar vector. We have V here, it's polar vector. We have um, field, the momentum. We have the electric field. So, and so on, many others as well. So these are called polar vectors, and then there are vectors which we call axial vectors or which we call pseudo vectors. Like they are the result of some rotation or action, and they are called pseudo vector. For example, for force we are having torque, which is a pseudo vector, not the actual or polar vector. Omega, then the angular momentum and the magnetic field. They are axial vector. Why we differentiate them? We differentiate them for reasons that they are pseudo vectors, they are axial vectors, because the actual vector direction under mirror transformation will be reversed, while the pseudo vectors or the axial vector don't reverse their direction under reflection. So the mirror transformation is not working here in the pseudo vectors. That's why we classify them in two different categories here. And this distinction between the actual vectors and the pseudo vectors, they are of prime importance, because in electroparity and other advanced topics, they play the key role while doing some calculations. Some here, when we say F equal to this, so F is perpendicular to V, F is perpendicular to B, and F is perpendicular to the plane which contains V and B. So if I consider here, now the plane is just like inside the boat here. So one edge is here, which is V, and then it is going into the boat, P is going into the boat. So we have the direction, we have the force direction is the plane here, and then this F is perpendicular, meaning the plane like this one, like the page here, and this F is perpendicular to this. So F is not only perpendicular to V, F is also perpendicular to B in that direction, and F is perpendicular to the plane which contains V and B with us. So if current is flowing in a straight line here in a wire, then we will move the magnetic field along the direction of the finger directions. So this is the current direction, and the fingers will be giving us the magnetic field direction, and vice versa. It is true other way around as well. Like if current is going like this in a circle, like in the direction of fingers, then the thumb will give the direction of the magnetic field. So if magnetic field going in a line, the current going in a line, the magnetic field goes around this one. If current is going around like this, then magnetic field will be upward. If current is going the other way around like this, then magnetic field will be in the downward direction. So the magnetic field is a result of the magnetic force, the result of a cross product here. So it will be in a direction which is perpendicular to the plane of both the components B and B.